All right, let me share my screen. Actually, let me play my slides first and then share. Okay, it's not going to let me do that. Great. All right, can you all see my slides? Yep, okay.
Yep.
All right, are they still there? Okay,
Yep.
actually, sorry, let me shrink this and then play. There we go. Okay. All right. So as Will introduced, I am Natalie Butterfield. I am a postdoc here at the Green Bank Observatory. I'm in my third year of my postdoc. I did my graduate work at the University of Iowa, where I mainly worked with VLA data, so radio data, but with higher angular resolution. And so I worked a little bit with some single dish observations, but really got into GBT observing when I became a postdoc here. And so today I'm going to be telling you about some high frequency GBT corrections. Okay, so just to kind of cover some of the GBT optics. So the dish is a 110 meter by 100 meter dish of a 208 parent parabola. All right, so that is what's shown here on the right, is that you can see what the parent virtual parabola is, so the 208 meter parabola, and that the GBT is a 100 by 110 meter section of that parabola. So the effective diameter is about 100 meters. So one of the nice things with the GBT is that it has an off-axis, so an unblocked aperture. So you can see that in the left figure. So shown here, you can see that the rays come in and the receiver cabin is set off with the feed arm. And so you don't have feed arms that are covering the dish as you would with, say, for example, the VLA, where you have the receiver sitting over the dish. And so the nice thing with the GBT is that it's an unblocked aperture. And so this helps reduce the side lobes and allow for high dynamic range imaging. Okay. All right, so one of the things that we need to have with doing high frequency observations is to have an active surface. So an active surface is where basically if you go back and you look at this figure here that's on the right, you see all of these different little squares or like blocks that are on the dish. And so each one of those is associated with a actuator. So each corner has its own little actuator, which is circled here in the picture. And so what these actuators do is they either push or pull each one of those different panel corners, and that is how you have an active surface. So the surface itself can be changed using these actuators. So the GBT has 2,209 actuators across the entire surface. And so with a good clear night with good corrections, we can usually get down to an RMS of about 230 microns. Okay, so using these actuators, this makes the GBT the largest single dish that's able to operate at these higher frequencies. And so down in the bottom, we have listed just a comparison of what the surface RMS is compared to the diameter for several different radio telescopes. So like the GBT compared with ALMA, the VLA, and then the future NGVLA. Okay, so we did some improvements to the active surface back in 2009. And so the top figure or figures, the different panels show the improved active surface across different months. So you can see that in January of 2009, you had a lot of deviations that were either associated with broken actuators. And so it really doesn't look like a smooth surface across it. And you can see that as the months went on, all the way to September, where the surface looks much better. And so these improvements to the active surface can really help what the beam pattern looks like. And so the beam patterns are shown in the bottom panels. So for each set of the observations at the very top, you can see what the associated beam pattern looks like at about 12 gigahertz. And so you can see that with the improved active surface, it really helps with the beam pattern that we can see. Okay, so the GBT achieves its theoretical beam at 110 gigahertz. So 110 gigahertz, that's up towards using the Argus instrument, so about 3 millimeters. And so the figures shown here illustrate what the beam pattern is for the 9 gigahertz. So that's X band on the left and then Argus on the right. And so you can see that the data that we're getting from the GBT really fits the profile fit, the Gaussian profile fit, which are the diamonds in both figures. And so there's more about this in the GBT memo 296. And so this really just demonstrates the success of the point and control system. And along with the gravity and thermal modeling of the active surface corrections. And I'll get into those in a little bit detail in the next few slides. So just a little bit of extra information. So the unblocked GBT aperture, which I showed in the first few slides, predicts that the first side lobe is around negative 27 dB. Okay. All right, so a surface with large.
Come on.
Okay, so the figure that's on the that is on the right is showing essentially what you would get when you're doing an auto OOF, which I'll show later. So this is showing you what the surface corrections are, whereas on the right, on the left, you're getting the receiver response. Okay, so modeling the surface. So to model the surface, we use what are known as Zernike polynomials. So these polynomials were first derived back in 1934 by Fritz Zernike, and they actually won him the Nobel Prize in 1953. And so these Zernike polynomials are essential for determining the beam optics. And so that's the patterns that you can see in the figure that's on the right, is the different Zernike polynomials along with the solutions that you would have for a dish-like surface. And then on the left, I'm just showing the equation for the Zernike polynomials along with the different values that you can get for using the Zernike polynomials. So essentially that's what we're using. Whenever we're solving for the auto OOFs, which I'll show later, you'll see Zernike polynomials for Z3, Z4, Z5, and Z6. And so I'll get into those a little bit later, but just to kind of briefly cover what we are using, we're essentially using Zernike polynomials. Okay. All right, so the Zernike gravity model. So one of the things that we have to account for, since the GBT is a moving structure and you can tilt the dish, is we have to account for gravity. So gravity can affect the surface based on the elevation of what you're pointing at. And so each Zernike polynomial is fit as a function of elevation. And so here are just some of the basic equation along with some of the coefficients for it. And all of this is discussed in detail in the 2014 gravity model note, project note 76. Okay, so the surface improvements with the Zernike gravity model. All right, so the figures shown here show what the efficiency is at different elevations. So the top left figure is showing the 43 gigahertz across different years with the improvements that they made to the Zernike gravity model. All right, so you can see that from 2003 all the way up to 2014 that the relative efficiency across different elevations has improved with the improvements to the Zernike gravity models that we're using. Okay, and then on the right, we're essentially just showing in the top right corner at 80 gigahertz, again, similar changes where from 2003 to 2004, what the improved efficiency is across different elevations. And so by including these surface improvements with the Zernike gravity model, we can improve the efficiency that we get, especially at lower elevations. And then lastly, the bottom right panel is showing what the errors, so the surface errors are by including what the Zernike gravity model. So essentially you want your errors to be as small as possible. So over time with this improvement, we can get better surface estimates or surface errors across the dish for different elevations. Okay. All right, so the surface improvements will depend strongly on the current thermal conditions. So it's not just gravity. Gravity is very important, but it also comes down to thermal. So you can have the dish is going to be heated over time, and that can cause deviations in the dish surface. And so you have to account for these in your total Zernike corrections. So you do have to include gravity, but thermal deviations are also important. And I will discuss that in a little bit more detail when I talk about LASSI, the new instrument LASSI, later on in the talk. All right, so auto OOF. So the use of the out of focus or the OOF mapping of a bright point sources to derive the Zernike parameters. So anytime that you're doing high frequency observations, so usually Ka band, so about 30 gigahertz or so or up, in order to get the best possible point sources, you need to do what's known as an OOF. And so this is where you're mapping a bright point source and using that to derive the Zernike parameters. So the figures down here show what the images would look like if your source was in focus, so that's the left panel, and then out of focus, either closer or further away. And so you can see that if you're in focus, that you have the best point source solution. And that's really what we're trying to get with our high frequency observations, to get the best angular resolution and point sources. Okay, so just to go over an example of an Argus auto OOF observations. So when you first do an auto OOF observations with Argus, your first and second scans are usually with the vein cal. So the vein cal scans are with the DCR, and usually you're doing the scan either with the vein and then on the sky. And so really what you want to have is about a value of like where your vein is about 3 times or so brighter than the sky. Okay, and then, okay, so then scan 3 is usually the first map in your auto OOF. Usually with your first map, you want to, at the default of the focus, you should see a good signal to noise for your first scan. So here the source is offset from the center of the map, which implies a significant higher elevation in your solutions. Okay, and then your second scan, so you're going to be doing 3 scans for your auto OOF. Your second scan, the counts are lower since the map was made out of focus. And so you can see that between these 2 images, you really have good signal to noise here. And then as you move to your second map, it's a little bit worse signal to noise. And then on your third map, then your OOF map is with a focus of about negative 12 millimeters. And it peaks higher than the plus 12 millimeter map. So the focus will be negative. All right, so you go through, usually those show up as you're going through each one of your different maps that you're making. And then you will get an image that looks like this in your Astrid window. Okay, so the images that are shown here is what the dish surface looks like. So I showed an image of something similar earlier in the talk, and that is essentially what your image will look like if it looks good. So if you notice in the top right panel, you'll kind of see the Zernike solution. So it'll say Z2, 3, 4, 5, and 6. The default is Z5, but you want to check and see what each one of your solutions look like. So you can do that by clicking on each of the different Zernike solutions, and it will show you what the map looks like. And at the bottom of your map, it will tell you what the surface RMS is. So for Z5 in this case, the surface RMS here is 136 microns. So you go through, you look at each one of your different maps, and you decide based on the residual RMS and the beam fits, which map looks best for your science. And then once you're happy with your map, then you want to send those solutions to the telescope. And so that's what the red arrow is showing, where you want to click that once you've decided which Zernike solution you're happy with. So again, if you're happy with 4, do not click on Z5 or Z3 and send those. You want to make sure that you have selected the solution that you want to send. So it will not automatically pick the best solution. You have to select which solution you want to send to the telescope. Okay, so this is the same kind of image, but instead you're clicking on the raw data. And so these are what the raw data will look like. So you'll notice that the top 2 rows looks very similar to the images that I was showing earlier. And the bottom shows you what your beam will look like. So you want to make sure that your beams look relatively good. You don't want to see any type of molted type of structure. You want to have very good beam shapes when you're doing these. So here's just another example. So for your fitted beam maps, you can see how the fits look different for the different Z solutions. And I think I'll show another image of this later on, but you want to look at all of your different solutions. You don't want to just look at the surface RMS or just the surface structure. You really want to look at the raw data and the fitted beam maps as well. Okay, so an example of good versus bad solutions. So these would be if you're looking at this image here, so Z3 through Z4, you might see something that looks like on the left, which would be an acceptable solution where you don't really get sharp deviations across the dish. You have a really low surface RMS, so this would be a good example of an acceptable OOF solution. Now on the right is an unacceptable OOF solution. So you'll notice that in this one, you get very sharp deviations across the dish. The surface RMS is around 600. And so this is an example of something that you wouldn't want to accept. If your solution looks like this, you do not want to accept any Z3, Z4, Z5 solution that looks like this. If it looks like the panel that's on the left, then that's fine. But if it looks anything like the one that's on the right, you do not want to send that to the telescope. All right, so another example of good versus bad solutions. So again, on the left is a good solution where you have very strong signal to noise. You have relatively nice beam patterns, whereas on the right, you get very low signal to noise. It's hard to see, some of the signals that are in there. The beam shapes in the bottom panels look very molted. You don't really get a good signal to noise for those. And so you wouldn't want to use a source that's like this for your OOF. You want it to be a bright source, and you want to have good solutions before you send anything to the telescope. All right, so just another example of a bad OOF solution. So in this case, these observations were done at the keyhole. So the keyhole is basically when the telescope is pointed directly up. So anything that's above about 85 degrees in elevation is the keyhole. And so the RMS for the solution was about 400. So not nearly as bad as the 600 we saw earlier, but still not as great as the 200 or so RMS that you would want your solutions to be. And so something like this, so a solution that has an RMS larger than 400 should not be used. And so you want to make sure that you check all of your solutions and you check your fitted and raw data beam maps to see what those look like. All right, so an example of a bad OOF solution with respect to the beam maps. So the observed beam should not be streaks or very elongated. So sometimes this can happen if you have windy conditions. Again, you want your beams to be relatively circular. You don't want anything that's going to be very elongated or streaky. And so again, these were associated with the data that was taken towards the keyhole. And so the apparent focus corrections were very large and had a very large elevation correction. And so if you do not trust the OOF corrections, if they look bad, then do not trust the results. So if you don't trust them, do not send them to the telescope, because the telescope will use that when it's taking the data. And so if you don't like the solutions, or if they don't look good, do not accept them and do not send them. So avoiding the Z3 solution. So sometimes the Z3 solutions can look okay, but in this case, you're seeing almost the streaks in this example here. So if you notice the Z4, which is the second to last row, and Z5, which is the last row, the beam shapes look relatively circular. But if you look at the Z3 fits in this case, you'll notice that they are streaky. And so you would not want to use Z3 in this example here. So, sometimes the higher fits can result in a better RMS and a better looking image. All right, so just to kind of briefly cover the CLIO status window where you would expect to see some of these values. So your as and L pointing corrections are going to be at the top there. Your focus correction, which you will get when you do your auto peak focus, is going to be as indicated here. The active surface is on with thermal corrections from the OOF, so you should be able to see that the active surface is on, and that the Vegas values, the balance values on the sky, are about -20 or so. So you can see that, not all of them are exactly 20, but roughly the J1 through J16 are around 20 or so. And so those are ones that you want to keep an eye out for. All right, so observing strategies and antenna optimization. So usually if you're doing high frequency observations, you want to do a point and focus correction, which is known as an auto peak focus, roughly every 30 to 50 minutes, depending on conditions. If you're at lower frequencies, so anything that's less than about 20 or so gigahertz, then maybe you could do it an hour and a half. And usually these point and focus corrections take about 5 minutes, and they should be included in your overhead when you're applying for telescope time. So when you're applying for telescope time, if you have a 3-hour observation, you want to make sure that you include time to do these point and focus corrections during your observation. An auto OOF takes about 20 minutes or so. Usually each of the scans are a little bit over 5 minutes. The 3 different scans that mapping scans that I was mentioning earlier. So those are a little over 5 minutes or so. And then you have to create and send your solution. So it takes about 20 minutes to do a full auto OOF mapping scan and data reduction. And that's used to do the correct for the surface and thermal effects at night. So you need to do an auto OOF if you're doing anything that's above 30 gigahertz or so, and you want to have the best possible point source solutions. So those take about 20 minutes. And then daytime surface changes. So usually if you're observing during the daytime, then it can be very challenging to do an auto OOF solution, just because the surface or the temperatures can change rapidly from across our timescales, and so it is challenging to do auto OOF solutions during the daytime because you need to do them very often. And so a lot of times, most of the time, if we're doing high frequency auto OOF solutions, you're doing them in the evening or at night. But as I will discuss later, one of the instruments that we are putting on the telescope is LASSI, which will hopefully open up some more daytime observations because it will be able to scan the surface much more rapidly. And I will discuss this later. So one of the things that you want to make sure that you do in Astrid, if you're doing high frequency observations, so above 20 gigahertz or so, is to make sure that you select heuristics to be relaxed. anytime that you open either Astrid or a new Astrid window, the heuristics will be set to standard. This is both for pointing and a separate window for focus. So you need to make sure that you open up the heuristics tab. So that's if you go to the very top, I believe you select either options or it's tools, and then you scroll down and you can select more options. And so the second tab that you have across the top is going to say heuristics. And so you want to make sure that you select heuristics to be relaxed. Anytime that you're doing high frequency observations, you need to do that anytime you open up Astrid for observations. So it will not default to relaxed. You have to set that. Okay, so lastly, last thing I'm going to discuss is LASSI. So LASSI is the laser antenna surface scanning instrument. So it is a new instrument that the GBT has currently been testing to put on the GBT. So it is a terrestrial laser scanner. So essentially what this means is that it emits laser signals that scan the surface, as is shown here in this picture. And these calculate the distances to the surface based on the time delay of the returned pulses. And so this is a way that we can measure what the surface looks like for the dish by scanning it rapidly. And so this will hopefully allow for more daytime observing at higher frequency because the processing time for LASSI takes only about 6 minutes compared to the OOF, which can take almost half of your observing time if you do it every hour. So hopefully with LASSI, we will be able to open up more daytime observing by being able to scan the dish more rapidly. And so that's kind of a brief overview of what LASSI aims to do. Right, so here is a photo of LASSI installed on the GBT. So it's going to be up above the receiver cabin and is pointed out over the dish so that it can scan the dish for the surface. All right, and then lastly, this is my last slide, just an image of what LASSI views when it is scanning the surface. So there's been some test observations of LASSI, and here is one of the images from the LASSI team about what the dish looks like. And so you can see that it looks very similar to some of the corrections that we've done with the auto OOF, but is able to do this in a much shorter amount of time. And so I will wrap up there. I think I'm almost out of time. And so I will take any questions.
Thank you very much, Natalie. There are no questions in the chat right now. If you do have a question, feel free just to unmute yourself.
What happens with wind?
You mean like when you're observing, or like if you're doing an OOF, or because usually if you're doing
either one.
Yeah, so usually if you're doing high frequency, the wind limits are much lower. Usually Tony will not schedule you if it looks like it's going to be windy, mainly because it can affect your observations. If the feed arm is shaking around, you know, it can really distort what your images look like. So usually you will not be observing if there's really high wind, but wind can affect your observations. And so on your CLIO screen, your status window, there is a bar which will show you what the wind looks like, along with gusts and what the average wind velocities are. So you just want to make sure that you keep an eye on it. And if it does seem like it's getting really windy, a lot of times they will stop or pause your observation, move to a lower frequency one, and you will be comped that time because of weather.
Couple questions in the chat about LASSI. So
Okay.
One is, when will LASSI become available for general observers?
So that has been I guess a question that I've heard before. Since I am not on the LASSI team, I'm not sure offhand. I think it's on the order of a year or two. If Andrew or Pedro is on, both of them are on the LASSI team. So they might be able to chime in and give a better estimate, but ballpark, from what I've heard, I think that's roughly the time frame that they're looking for.
Yeah, I don't see Andrew or Pedro on right now.
I do know that the project is entering. Oh, Dave, are you on? Yeah, I'm on. Yeah, it's gonna be a year or two. We have to figure, even if when they get Lassie up and going, they have yet to take a measurement to prove that it actually can and prove the surface in terms of on sky with the source. So we still need to commission it, and once it's commissioned, we have to figure how we're going to deploy this in a way in which users can use this in an operational sense. So the operational plan of the use of Lassie is still a little bit up on the air, and it depends on how the performance and how well things work. So and Natalie's right. We're talking a year or two out after commissioning.
Here are two other Lassie questions. One, will Lassie improve the efficiencies compared to oofing?
That's another interesting question. Long term, yes. Short term, not really, because the current way they're looking at it is they're using an OOF, and it's going to set a reference scan, and the Lassie measurements will put the surface back to where the OOF was. So in that sense, you just maintain your good aperture efficiency or maintain your surface throughout the night. When I say long term, I think yes, because I think we can hopefully use the Lassie to help improve our gravity models and everything underneath, basically. And that's where it's still, from my point of view, it's a little open-ended in how we'll end up using Lassie in a sense, because we could end up using it to build all these underlying models, and then we might take quick scans. We might not have to do a full Lassie scan, for example, to measure the full surface to understand how the surface is changing, because it's only really a few Zernike's. That Z4 term really changes a lot, and that's pretty temperature dependent. And that will, but anyway, so with Lassie, I think, and taking more data, I think we'll be able to build the models on which all this is based on, make those better. So that would improve the general aperture efficiencies. But yes, in principle, yeah, we should make things better having Lassie than not having Lassie. But how much we improve, it's not going to improve things immensely, because we're already approaching sort of our theoretical limit that we can get to based on the subreflector and the gaps between the panels. But we can, the idea is to increase the amount of time in which we have good aperture efficiency with the telescope. That's the main goal, more so than being able to vastly improve the aperture efficiency of the telescope, because we're already getting there. So if we take the OOF corrections and we measure right after the OOF, we have pretty good aperture efficiency. The problem is when the surface changes, then you lose your aperture efficiency. And if it's changing so rapidly, you'd like to be able, especially during the day, you would like to be able to correct that surface. And oofing takes longer than it's the time scale of oofing is similar to the time scale in which the surface is changing. So we need to find quicker ways in which to measure the surface changes and make corrections on the telescope. So that's a long-winded answer, sorry.
One last question before we move into Tony's talk, and then there are a few more that we'll answer in the chat. But if none of the solutions for auto OOF are acceptable, does that mean that the surface is too bad to observe? Should we reanalyze the OOF, continue without sending, or abort the whole scheduling block?
You can, this is a little bit science dependent. What I do is I actually look at the aperture efficiency with just the default gravity model. A lot of times that works really well. You're not too far off. You might lose 20% on your aperture efficiency. So instead of being 40%, let's say you're 35% or 30%, which is still good enough to proceed. If you're doing extended sources, fluffy ISM sources, and spectral line work, then a surface isn't as critical as if you're, targeting a point source and doing point source science. So it depends a little bit on your science. I will say a lot of times if you have an option, somebody asked on winds, it's useful to do the OOF at a lower frequency, like Ka band, if that's up on the telescope, because there the beam is bigger. The winds can affect the oof. A little bit of wind, a little bit of jiggle while you're taking. If you have a gust of wind comes on in the middle of one of your oof maps, that can really, I mean, just one little gust of wind can mess up the solutions because the software doesn't know that the feed arm changed. So it tries to move those actuators to make that, you know, that data to induce a point source, even though it's not a point source when the wind is jiggling it around. So if you observe at K-band, the beam's bigger, you're not as sensitive to the winds, and they have this, we have this Caltech Continuum back-end receiver that does really fast switching, and it improves the signal noise immensely. So the sources are brighter. There are more sources on the sky that you could oof at Ka band. You could do somewhere 50 to 100 sources on the sky easily with Ka band. But for Argus, there's really only 4 to 5 good sources one can use to get good signal to noise oof observations.
Okay, thank you very much, Dave. And thank you, Natalie, for a very informative talk.